Okay, let's dive in. We got some really interesting source material today you brought, all about the search for life out there, specifically looking at exoplanet atmospheres.
Right. And the traditional way, well, it's always been about following the water, hasn't it?
Yeah, exactly. Looking for those chemical fingerprints, biosignatures like oxygen or maybe methane,
Usually by watching a planet pass in front of its star, the transit method. You try and see what light gets absorbed by the atmosphere.
which is where instruments like JWST come in, right? Trying to sniff out those gases.
Precisely. Analyzing that starlight filtering through.
But the kicker in these sources, the really surprising bit, it's about clouds,
Ah, yes. Clouds.
which, for ages we've just seen them as a problem, a major roadblock, basically, getting in the way.
They certainly are for transit studies. I mean, they're opaque, they scatter light like crazy. That's me scattering. It weakens the signals from the gases underneath.
Makes it super hard to see what you're looking for.
Exactly. They've been a real headache.
Okay, so here's our mission for this deep dive based on what you've shared. How could clouds, these things we thought were obstacles, actually turn into, well, allies, especially for future telescopes? How does that flip happen?
It's a great question. So, yeah, transit spectroscopy, the standard method, is powerful, but those clouds are a genuine issue. You're looking for combinations like, say, oxygen and methane together.
Which on Earth hints strongly at life.
Right. But if thick clouds are blocking the view through the atmosphere, you could miss those signs completely.
Okay, that makes sense. For transit, you need light through, cloud stop light. Simple enough.
Exactly. But here's where the sources introduce a different angle, direct imaging.
Right, direct imaging, that's where you try to block out the star itself to see the planet directly.
That's the one. You use something called a coronagraph, a specialized shield, basically to mask the star's intense glare.
Allowing you to catch the faint light bouncing off the planet.
Precisely. The light reflected off its atmosphere, maybe its surface. It's incredibly difficult technically.
I bet. Which is why it's not how we've found most exoplanets, right? The sources said 1.4%.
Yeah, a tiny fraction. The planet is just so much fainter than the star, millions, billions of times fainter sometimes.
Okay, still sounds incredibly hard. So where do the clouds come in to help here? That's the counterintuitive part.
This is the core idea from the new simulations. They use a really sophisticated model, CARMA.
Community aerosol and radiation model for atmospheres.
That's it. And those simulations suggest clouds can actually boost the signal in direct imaging.
Boost. How? They're still opaque, aren't they? If they block light going through, wouldn't they block light reflecting off too?
But think about how you see clouds from, say, an airplane. They're bright, right? Because they reflect sunlight really well.
Okay, yeah. Very reflective.
So the idea is these exoplanet clouds act like, well, giant mirrors in the sky.
Mirrors. Huh.
They scatter a lot more starlight back towards our telescopes than a clear atmosphere would. More photons, basically.
So more light bouncing off means a stronger signal overall.
Exactly. And that stronger reflected signal can help amplify the faint signatures of gases like oxygen or ozone that might be present above the clouds or maybe mixed in near the tops.
Wow. Okay, so the same property scattering light that messes up transit viewing.
Actually helps when you're looking at the reflected light in direct imaging.
That is fascinating.
Yeah.
It's about the method changing how you interpret the physics. So the big question becomes, could these troublesome clouds actually be our friends for direct imaging missions?
That's precisely the question, and it's what a study out of the University of Chicago really dug into.
Okay, tell us about that. Who was involved? What did they do?
It was led by a graduate student, Huanzu Yang, working with Michelle Hu and Professor Dorian Abbott, and they used this really clever kind of two-step simulation process.
2 steps. How did that work?
Well, first they used that CARMA model we mentioned.
Build the clouds.
Essentially, yeah. To simulate how clouds and aerosols would realistically form and spread out in an exoplanet atmosphere under different conditions. So they got a good physical model of a cloudy atmosphere.
Right. Step 1, make realistic computer clouds. Then what?
Step 2, they took those cloudy atmosphere models and plugged them into another model called PSG, Planetary Spectrum Generator.
Okay.
And PSG calculates what the light reflecting off that specific cloudy atmosphere would look like to us, the spectrum, including any signs of gases like oxygen or ozone mixed in or above those clouds.
So simulate the clouds, then simulate the light bouncing off them to see what chemical clues we might detect.
Sounds thorough.
It really is. And their main finding It's been accepted by the Astrophysical Journal, by the way, is pretty
What
significant.
did they find?
They found that having those clouds can actually increase the signal-to-noise ratio enough to make spotting oxygen and ozone with direct imaging significantly more achievable.
More achievable, even for planets really far away. Yes, even over interstellar distances. The clouds basically make the faint biosignature signals stand out more against the background noise.
That's huge. It totally changes the game for how we might search for oxygen, especially using direct imaging. The obstacle becomes the amplifier.
And this has some really practical consequences for, planning future space missions.
How so? How does it affect things like the Habitable Worlds Observatory?
Well, it reshapes the whole target list strategy for missions like HWO, which is planned for the 2040s, or even the upcoming Nancy Grace Roman Telescope.
Which has a coronagraph component, right?
It does. For both of them, this study suggests they shouldn't necessarily shy away from potentially cloudy planets anymore. In fact, for direct imaging, those cloudy planets might be prime targets.
Might actually look for the cloudy ones. That's a real strategic shift.
It could be. And it also applies to the huge ground-based telescopes being built, the ELT, GMT, TMT. They might be particularly good at looking at larger rocky planets around sun-like stars, where clouds could give that reflective boost needed to pick out biosignatures.
So does this mean we should go back through the list of known exoplanets, the ones we maybe thought were too cloudy to bother with?
And reconsider them for direct imaging? Absolutely. That's the immediate implication. It forces a reevaluation.
It really feels like this connects to that bigger shift in exoplanet science, doesn't it? Moving beyond just finding dots of light.
Definitely. We spent decades getting good at just finding them, transit radial velocity.
Counting them up.
Right. Now the focus is shifting hard towards characterization. What are these worlds actually like? What's in their air?
And this study suggests our previous models might have been too pessimistic, at least for direct imaging.
That's a key point. Cloud-free models, which are simpler to run, might represent the worst-case scenario for detecting biosignatures in reflected light.
The lower limit.
Exactly. Real atmospheres are often cloudy, we think. So reality might actually be more favorable for detection with direct imaging than those simpler models suggested.
Wow, so clouds aren't just, scatterers. They're part of the climate, maybe hinting at water cycle.
Critical factors for habitability in themselves.
And now they might also help us see the signs of life itself.
It's a fantastic example of how science progresses. You look closer, you use better tools, maybe a different technique, and what seemed like a problem, well, it gets reframed.
It becomes part of the solution.
Researchers are really set up now to use clouds maybe as an asset, not just a nuisance.
Okay, so wrapping up this deep dive then, the big takeaway from these sources seems to be clouds, long seen as a pain for finding life on exoplanets,
Especially via transit.
might actually be incredibly helpful when we use direct imaging. They act like reflectors, boosting the signal, making biosignatures like oxygen potentially easier to spot.
It really could change the strategy for future observatories.
It's a surprising outcome, really. You wouldn't intuitively think blocking the view helps you see better.
Science often throws up those counterintuitive results. It's why we keep digging, keep refining our methods and models.
Which leads to that final thought from the sources, something for you, the listener, to ponder. If clouds, an apparent obstacle, can turn out to be an asset for finding biosignatures, what else is out there? What other things that seem like challenges in the search for life right now might, with a new perspective or new technology, turn out to be helpful clues in disguise?